Hey guys, you have your very last video because I will be back in class on Monday. I'm sure y'all are so excited to not have to listen to me anymore. You can actually see me now. So let's think about what we did last class. So last class we talked about making a scatter plot. We talked about a direction, form, and strength. That would be how to interpret a scatter plot. And we also talked about correlation, how to interpret that. So today we're going to extend our lesson on linear regression. And we're actually going to talk about what's called a regression line, or maybe it's called a prediction line, or there's lots of different things. By the end of class, we'll end up calling it a least squares regression line, and we'll explain how that works in a little bit. So if you have a set of data, say you have a scatter plot, so no, I don't have a scatter plot on this page. Oh, here we have one on the next page. And so here we have a scatter plot. So if we have data that we assume the form to be linear, then what we want to do generally with this data is we want to find one linear equation, one straight line, that would be the best prediction, the best fit for all of these data points. So what we have here, if we look at this graph that we have right here, we have our data plotted out in a scatter plot, and then they've actually gone through and calculated, and it's a really fancy way, kind of like with regression, this line that would best approximate the data. You know, you want to, most of the, or about half the points below, about half the points above. It's a pretty complicated way how they figure out where the best place to put the line is. A little above our heads, actually. But just like before, what we're more interested in is understanding what this line means, what it can do. So let's go back and talk a little bit about some of these vocab words. So generally, your regression equation is written like this. It's written as y hat, and there's an important reason why that hat, why the y has a hat on it. It's kind of funny to say. And let me write the equation. I'll explain to you everything. And then we generally are going to write it as a plus bx. Now, y'all are so used to seeing y is equal to mx plus b, where b is your y-intercept. But the way that it's generally written in AP Stat, in your textbooks and on your AP formula sheets, is that b is your slope. And this will run all throughout the class. We'll really need later for b to be the slope, so we're just going to start off with it this way and use it like this. All right, so let's talk about all these different things. Y hat is going to be your predicted value. This is like your y. From the given data. Okay, so think back to when we talked about the normal distribution, and we started using these funny letters for mean and standard deviation. This is kind of a side note, but it'll help you to understand why that y has a hat on it. Okay, so we use these funny letters, mu and sigma. Mu is for mean and sigma was for standard deviation. And why I told you that we did this is because we needed different letters to represent the population values, or the value for everything, and then we had other letters that represented that it came from a sample. Well, whenever we're talking about a prediction equation or a regression equation, this is always calculated from a sample of data. You're given, a sample of, I think that today we're going to talk, or last time we were talking about body weight versus pack weight. We're given a sample of people, and we want to look at their body weight versus the pack weight that they carry. And we're not going to look at every person in the whole world. That would be, or in the whole U.S., or whatever group you're looking at, that would be your population. So since this is taken from a sample, we put a hat on that Y. When we talk about, kind of making it go on to the whole population, then we would take the hat off that y. And just y by itself would be for the population. Y hat is for a sample. AP is really ticky. They always want you to put that hat on your y. And if you don't in cases, you could get points taken off. Okay, A is your y-intercept. And then B is your slope. Slope is always going to be the number in front of your x. It's always the constant in front of that x value. Here, I give you a little more information about y hat, b, and a. We are going to have to interpret these. So these definitions right here that you have, especially for slope and y-intercept, are going to be what you use to interpret. But of course, remember that when you interpret something, you always have to put context in with it. And then we're going to talk about extrapolation and a residual plot in just a little bit, so we'll go over those later. Okay, so here it's kind of the same thing I went over before. It's kind of a repeat of itself. But here's some interesting information about that equation for slope. It says here that this is going to be what you get on your AP formula sheets. B sub 0 plus B sub 1 times x. But just remember, whatever the number is, whatever's in front of this x here, this is always going to be your slope, and then the number by itself is always going to be the y-intercept. Okay, so let's take this data. We are going to actually learn today how to calculate a regression line, but we're going to calculate it on our calculator. So what I'm interested in doing is I'm interested in taking this data right here, the NEA change and the fat gain, and putting it into L1 and L2 in your calculator. So we're going to take the NEA change and put it in L1, and the fat gain and put it in L2. And there's no reason that there's two rows here except that they couldn't fit all the data on one row. So when you get here to 355, just go on and continue putting these data points in your calculator. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 16 x's, or 16 in L1 and 16 in L2. Alright, so pause the video, get out your calculator, input this data, and then we'll come back in just a second and we'll calculate a regression line. Okay, I have my data in my calculator. We don't need any of that. And what we want to do is we want to figure out what our regression line is going to be. So we have a function in our calculator that will calculate this for us. You may have done this before. So what we're going to do, you should have all this data in L1 and L2 in your calculator. So what we're going to do is we're going to press Stat. We're going to go over to Calc. This is the same place where we did those 1-var stats, where we did mean, standard deviation. You see right here number 4 on the calculator that says linreg, but this says AX plus B, and I told you that the slope had to be B, and it's going to make it easier if we do it the other way. So we're going to scroll down, that way there's no confusion, and if you go to number 8, it is A plus BX. And so I'm going to hit enter on number 8. You get the same answer no matter whether you use 4 or 8. They just switch around the variables. So, I mean, as long as you write the equation properly, it really doesn't matter. But B for later really needs to be slope. Okay, so now you need to tell it what is your X list and what is your Y list. The X list always goes first. So our X list is L1, so we're going to press second 1. And then we separate the two lists by a comma. Comma is right above the number 7. And now we want to put in the Y list, which is L2. And then we hit enter. So this gives me my regression equation. Let's make sure I got it right. Hold on. Okay, yeah, that looks pretty much right. Yeah, exactly. Now your calculator may have R squared and R on it. We're not interested in those right now, so don't worry about whether it does or doesn't have R on it. We'll talk about that later. All we really need are the slope and the y-intercept. So you can see how to calculate both of those. Slope and y-intercept both have really nasty formulas. I didn't even give you the formulas for them because we won't have to calculate them by hand. You won't have to recognize the formula, so don't worry about it. We're now interested in how can we write out our equation, and then how can we interpret the slope and y-intercept. Okay, so I'm going to minimize that. So we have our equation here. Notice that they don't use y and x. They use what actually y and x represent. Whenever you are writing out an equation like this on the AP exam, you kind of have two options. You can write your equation just like this, the way they've done it, or you can write it with y and x, but then underneath you have to tell the person, tell the test, what y and x actually are. So you could say, you know, y hat is equal to 3.505 minus 0.00344x, but then you would have to say that y is fat gain and x is NEA change. Oops. All right, so now let's talk about interpreting. Okay, so what the slope tells you and what the definition says. For every unit, 1 unit of increase in x, the y goes up, whatever the slope is. It's exactly everything that you've learned since pre-algebra when you learned about rise over run. You know, if your slope is your rise, the point negative 0.00344, then your run would be the denominator. You know, any number that doesn't have a denominator, the denominator is always 1, so your run would be 1. So your slope is going to be how much the y increases for every, or decreases, depending on whether it's positive or negative, for every 1 unit increase in x. So what we say, the slope b equals negative 0.00344 tells us the amount of fat gained is predicted to go down 0.00344. It's predicted to go down because it's negative for each added calorie. So for every 1 unit of increase in x. And remember, you always have to put context in whenever you're interpreting. Now the y-intercept tells you what the y value is when x is 0. Now sometimes this will make sense and sometimes it won't. Say we're looking at, say we measure everybody's height and we measure everybody's arm span. And we do height on the x-axis and arm span on the y-axis. Well, say we get a y-intercept. I'm not quite sure what the y-intercept would be, but we get a y-intercept probably fairly close to 0, but not exactly. Now, the y-intercept for that problem would make no sense at all because you wouldn't have an arm span for someone with a height of 0. You can't have a person with a height of 0. So, in some cases, they'll say, you know, why doesn't this make sense? And you just have to look at the context of the problem to see why it doesn't make sense. Okay, so now let's take a look at this example problem down at the bottom. So what I want y'all to do is pause the video and then come back, work the problem out with a partner, interpret the slope and y-intercept. You can use this over here as a guide, and then come back and I'll give you the answer. Okay, so here we go. So we have, they give us the equation for acid rain over a 150-week period. And so they ask us to interpret the slope and y-intercept. So for every increase of 1 week, oh, I screwed this up, so let me fix it. The pH value is going to decrease 0.0053. And now my sentence is much shorter than theirs, but I still talk about context. I say the word pH. And I say, for every increase of the x value, and I don't need to say x value, I need to say what the x value actually is, and that would be weeks. And then the pH, I say what y is, so y is going to decrease or increase. All right, so now in this case, we actually have a y-intercept that does make sense. So this is going to be the pH at the beginning of the study. So this is going to be at 0 weeks. When x is 0, x is the number of weeks, that's going to be our y-intercept. So we have a pH of 5.43. All right, so let's go back. Let me see, I think we're on page 3, yeah. So now let's talk about predicting. This is really simple. This is pretty much just basic algebra for you. So what we want to do is we can actually use our regression line to predict values. So say we have a value for the NEA change, the X. And we want to predict for this given NEA change what the fat gain would be. So all we have to do is plug in the x value into our equation, do the math, and we get our prediction value. So it's pretty straightforward. The one thing that you have to worry about is what's called extrapolation. So let's go down here and look at this really quickly. Okay, extrapolation would be where you are trying to predict a value that is outside the range of x values that you're given. So the data that you're given is going to be what you're using to calculate your prediction equation. Now, if you have values for really small or really large x's that are outside of this range, they could, if you actually had data for these points, they could pretty drastically change your prediction equation. So you only want to predict values that are in between your smallest x value and your largest x value. So only predict values between smallest and the largest x. All right. So up here, if we look at what they tried to do, if we look at our data, let's go up just a little bit. Our smallest value for non-exercise activity is going to be, let's see, about negative 100 or so. And the largest non-exercise activity would be about 700 amount of calories, I guess. So they want to see, they have a non-exercise activity calorie level of 1500, and they want to try to predict weight gain. Now, this doesn't really make a lot of sense because our values only go from negative 100 to 700. So we really don't have an idea of what would happen at 1500 calories. So we cannot use this prediction equation to calculate it. This would be what we call extrapolation. I ran out of room. All right, so the last thing that we want to talk about today is what are called residuals. And what's called this word, the least squares regression line. Okay, so here we have some data. Don't worry about putting this in your calculator. We're just going to look at the graph that they give us. And so what it is the same data we looked at before. The body weight versus their pack weight. So we're interested in how our data varies from the line. And how our line is actually calculated, we can kind of visually look at how it works. So let's talk about that on the next page, actually. So first, let's talk about residuals. Residuals, we have one residual for each data value that we have. And the residual is all it is it's the difference between your data point and the line. And this distance can be positive or negative, depending on whether your data point lies above or below the line. So remember, you have one residual for each data point, and all it is the y value that you're given. This would be your given y, data that you've actually collected, minus your predicted y, and this would be y hat. So generally how it's going to work in your questions is that they're going to give you an x value, or they're going to point you to an x value in the data that they've provided, and then they will give you the y value that goes with it, and then they want you to calculate the residual. They're not going to give you y hat. You're going to have to calculate y hat on your own. So let's look at this example. They want to find and interpret the residual for the hiker who weighed 187 pounds. And so the first thing I want to do when I calculate a residual is I want to find the original point. So I need an x value, that's 187 pounds, and then I need a y value. Okay, so let's go all the way up. They give me the data up here. I find 187 pounds. And they had a pack weight of 30 pounds. So this is going to be my y. Alright, so now I need the prediction value. I need my y hat. And I actually have to plug that into my prediction equation and calculate it. And that's what they've done here. So their prediction equation, they gave it to you, was 16.3 plus 0.0908. And multiply that by 187 and you get 33.28 pounds. So here is my y hat. Okay, so now what we're going to do is we're going to take in the formula that says y minus y hat. It always needs to go in that order, or if not, then you'll have an incorrect sign. So what we're going to do is we're going to take and we're going to do y minus y hat. That's what they've done down here. So our y is 30, that was what we got from our data point. Our y hat is what we calculated, that's the 33.28. And when we subtract them, we get negative 3.28 pounds. And then they also ask you to interpret this. And when you interpret, you just want to state, what it means in the context of the problem. So what this means, I don't know why never mind. What this means is that our equation has underpredicted. Oh, sorry. Okay, no, I got this backwards. Since our point is below the line, that's what happens when it's negative, then our regression line is going to overpredict the hiker's pack weight. So if you have a point that's negative, then the line has over-predicted it, because what happens is, like here, you have a data point. The residual would be this distance right here between the 2 points. And if that value is negative, then your data point lies below the line, and so negative would be over-prediction. And then if you have a data value that lies above the line, like this, here would be your residual, then this would be under prediction, because it would be too low. It didn't want to write for me. Under prediction. Okay, so let's talk really briefly about the least squares regression line. And then I have given you some information on the bottom here about calculating your least squares regression line. So we've already done that, so if you need to look back at it and try to remember how to do that on your calculator, you can look at these boxes in the middle of the page. Okay, so let's talk about how the regression line is actually calculated. And the visual representation is kind of the easiest way to do it without thinking about these big nasty equations. So what they've done is they've just really tried to kind of give the smallest residuals as possible. And that doesn't really work so well since residuals are only in one dimension, and we have two dimensions here in our graph. So what they've done is they've taken and they've made boxes out of all the residuals. You can see all these little boxes. And how the line is calculated is that they've made these boxes all together have the smallest area possible. That's why it's called the least squares regression line, because they've taken all those residuals and squared them and then made those values as small as possible, the sum of all of those. And so that's where the line comes from. Geometrically, that's how it's placed on the scatter plot. Now, algebraically, it's pretty complicated to try to get the formula together. So we're just going to kind of trust the information that we're given and trust the calculator. All right, so you have a bunch of example problems over on the next page. So what I'd like for y'all to do is get together. You should still have plenty of time in class. Work out these 4 example problems, and then whenever you get done, come back and I'll show you the answers. Okay, so let's take a look at these solutions. I hope they're big enough that you can see them. Let me make them just a little bit bigger. It's probably better. Okay, so we've interpreted slope, right? For every increase in 1 city mile per gallon, the highway mile per gallon increases by the slope value. Interpreted y-intercept. Here is one of those cases where it's not meaningful, because you can't have a car with 0 miles per gallon. It wouldn't go anywhere. Right, so, and then if you look at those two right there, you can see the 2 prediction values. The next one is another prediction value. This is kind of tricky because they don't give you the number, they just say at the end of the study. So the end of a study is 150 weeks, right? So then you would just plug in 150 for X. The last one, I want you to pay close attention to these 2 bottom ones, or to this one first, then we'll look at all the rest of it. Here they want you to calculate this residual. So I had a lot of students that, I guess this is something that they had a hard time with, was calculating residuals. So make sure you get the y that you're given. You predict y given x, that's your y hat, plug it into the equation, you subtract the 2. And then here it's negative, so my equation overestimates it because the line is going to be above my point. Okay, so up here, all I've done is taken the data, put it in my calculator, and drawn a scatter plot. Here I've given you the equation, but I've also given it to you in terms of, I need to do this right here. In terms, I put a hat on my metabolic rate. In terms of the x, what x and y actually are, in terms of the context. I've interpreted, right, my slope. I'm probably pretty tired of that by now, but you also have some homework over it. I've predicted my value for 45. And then for E, I've calculated the residual for 48.5. Here, they didn't give you the Y value in the question. You actually had to go up and find it in the data set and pull that Y value out. That's where I got the 1396. And then you calculate Y hat for 48.5. And then you go through, subtract Y minus Y hat. Here, once again, it's I can't talk. This has underestimated because it's positive, so my point is going to lie above the line. Okay, so we will talk more about your test and all sorts of things when I get here on Monday and Tuesday, whatever day you have me. So your Unit 2, Day 2 homework will be due next class period, so make sure you have that with you. And that's pretty much it. I will see y'all next week.